Hello, this is Jennifer Martinez, and in this section we're going to introduce vector equations and show how they are related to our augmented matrix. A vector, sometimes called a column vector, is an ordered list of numbers, or a one-column matrix. So let's let U be a vector. I'm going to denote U, the vector U that is, with an arrow on the top. This is a common notation for a vector. The book just denotes it as a bold letter. That's another common notation of a vector. So what does U look like? Since it's an ordered list of numbers, it can be in n tuple, or it could represent a one-column matrix. A n, that's the number of rows by one matrix. This is if U is in Rn. I added the Rn here. What is Rn? Well, R is the set of all real numbers. So Rn is the collection of all lists of n real numbers. You can write Rn as a set. So writing it in set notation, Rn is the set of any vector here, where the v1, v2, and vn is in R. So that's why this is Rn, because each element needs to be in R. And you can see that Rn is the set or the collection of all lists of n real numbers. So let's look at description of R2. A list of two entries is an ordered pair, so we can consider the geometric description of R2 to be our rectangular coordinate system in the plane. Because each point in the plane is determined by an ordered pair, we can identify a geometric point AB with a column vector AB. So this is how it's listed as an ordered pair, and then this is how it's listed by a one-column matrix. So we regard R2 as the set of all points in the plane. Here is a few examples. So the point 2, 2, here it is as an ordered pair. So now the 2, 2 point is going to be determined by a vector. What we're going to do is we're going to do a ray from the origin up to that point, and that line right there is the vector. And if you know anything about vectors from physics or your past calculus classes, you know that they are free to move about in space. So we're going to see in R2 that what's important about this vector is the direction and the length. So this is two different examples of how we can visualize vectors in R2. So now we're going to look at how we add vectors in R2. We're going to add vectors using the parallelogram rule for addition. If U and V in R2 are represented as points in a plane, then U plus V corresponds to a fourth vertex, this vertex of the parallelogram, whose other vertices are U, 0, and V. So you can see it's going to be the diagonal of the parallelogram. How I like to think about this is we're going to start with U, and we're going to add V. So if this is V, if you remember, it doesn't remember the space placement, does not remember just the length and the direction. And so then you're going to go from the beginning to the end, the start to the end, to get to U plus V. So you can see that that would be the diagonal of the parallelogram. You can also do V plus U. Addition is going to turn out to be commutative, and that would give you to the same point. So let's look at an example. Let's let U equal 3, negative 1, and V be 1, 2. Find U plus V. So graphing these 2 points in the two-dimensional plane, we get that U is 3, 1, negative 1 as an ordered pair. And I'm going to represent it as such. So that is U. And V is 1, 2, the first quadrant here, represented by that point. So the addition would be the vector from the origin out to the diagonal of that parallelogram, it looks like that point is 4, 1. So that would be the addition of u plus v. And notice if I do take u plus v, and if I add the entries, 3 plus 1, -1 plus 2, that would be R4, 1. So you can see here, to add vectors, we're just going to add the entries, assuming that they're the same size. So let's look at an example in the book. So let's let that u be 3, -1, just as it was over here. And now let's display the vectors u, 2u, and -2/3 u on a graph. 2 is a scalar, and 2u is called scalar multiplication. And what scalar multiplication is going to do is it's going to stretch everything, the whole vector, by 2. So we want to multiply 2 times the 3 and 2 times the -1 to get 6, -2. To display this on a graph, 3, -1 is right there. And you can see 2 times it would be 6, -2. That whole vector there. So u is in blue right there. There's u. And in orange there is 2u. -2/3 u would be multiplying everything by -2/3. So not only does it contract, it changes the directions as well. So this would be now a -2 and a 2/3. So -2 and 2/3 is about right there. -2/3 u is in green there. So you can see it's going to be all along this line. Y equals -1/3 x, or how it's displayed here, x2 is -1/3 x1, depending on if you call this y or if you call an x versus x1 and x2. Vectors in R3 are going to have 3 entries, or a 3 by 1 column. Here's an example of a vector A, and in bold, 2, 3, 4. They represent geometric points in a 3-dimensional coordinate space with arrows from the origin, sometimes included for visual clarity. So here they have a vector A, there, 2, 3, 4. 2a, the vector A and vector 2a are displayed in figure 6 here. So 2 times it would be stretched through, and we can see here that 2a is going to be 4, 6, 8. Properties of vectors, the algebraic properties for all u, v, w in Rn and c and d scalars. Here's all the properties. It's commutative, it's associative. 0 is the identity. By the way, 0 does not mean the scalar 0. It's the vector 0. It's in bold there. So it means a n by 1 matrix with n entries. If you had a 0 in R3, there would be 3 zeros in your vector. And you don't need to specify this. I have seen 0 in sub n here or sub 3, but you're just going to make your 0 whatever size you need. Number 4 is the inverse property. Number 5 and 6 are the distributive property, but notice that C is a scalar multiplied by 2 vectors, or a vector with 2 scalars. And the same thing here, you have associative with all vectors or with 2 scalars, and then this is the identity property for multiplication. And you can prove these all very easily. Let me just show you the first real quickly. So let's let vectors u and v be in Rn. So where u is going to be u1, u2, and un, each one of these is an R. That's what that means. And v is v1, v2, and vn. So this is what u and v in R means. And these are just R. We know things about R. So when you add u plus v, you add all the entries. And you know each entry is commutative because we know that in our algebra. We know things are commutative in R, which, by the way, is what v plus u is. And you could do the others in a similar fashion. That's the proof of just one. So let's go ahead and try one more. What about number 5, the proof of 5? So again, I'm going to let u and v be in Rn and c be a scalar. Again, where u is and v are these n by 1 column matrices. So now I want to see if distributive property works with a scalar. So I'm going to take c times v plus u, or u plus v. And I'm first going to add. So we know that scalar works with one matrix by definition. And we can multiply each. Now, each entry are just a scalar times 2 real numbers. So we know that works. And that looks like the addition of the first CU1, CU2, all the way CUN, this matrix, plus CV1, CV2, all the way CVN, which, by the way, is just CU and CV. And we have the right-hand side, CU plus CV. And this can be done with ordered in tuplets as well. So I'm going to stop here. In our next video, we're going to look at linear combinations. And linear combinations is where we're going to relate vectors with vector equations. This is called a vector equation. And our vector equations are going to be related to our augmented matrix.